Pranab Sen is only arriving now in the morning. So that's why we didn't want to have him in the morning session to make sure that he arrives in time. So I will take the slot after Eric, and then Pranab has the, then we have a special extra lecture in the afternoon by Pranab, because we had to shuffle a bit, so it's the only one in the afternoon. And yeah, that's it. So it's kind of, it's a slight change from the initially circulated program. I think, well, we can start now. So
sure. Okay. Okay. There's still a tutorial session after the Pranab's talk. Yeah. Okay. All right. Okay. Well, if you're following along on the proposed syllabus, you can see that we're slightly drifting behind a little bit, which I mean I think is okay because you guys seem to be interested in this and asking questions. So we'll try to hit that mark of the syllabus, but you know, just it's more important that you guys are absorbing this and understanding it. Okay, so yesterday what we did is we looked at the distinguishability conditions for separable operations. Right? We looked at all those different cases. And for the first third of the lecture today, we're going to look at the LOCC conditions, and then we'll put it all together and we'll draw some comparisons between the two. And we'll see some explicit examples where we have this separation between LOCC and separable for two-qubit ensembles. Okay, before I begin, I just wanted to see if I have the references here. Right, so I wanted to list where this is coming from. So I'm not just pulling this out of thin air. This is all coming from work that's either on the archive or already published. So the first is the Walgate paper. And I mentioned this previously, but this is in PRL. This was published in 2000. And then another one that we'll look at today is almost a follow-up to this paper. This is by Walgate and Hardy. And this was in 2002. And then the separable problem was pretty much solved by Ranyao Duan and collaborators. And this you could find in IEEE IT. And this is in 07. And then some of the other pieces that you won't find in there is just some recent work that I've done with Ranyao and Minshu Xie. And this you could find in the archive of, let's see here. So all the notation and just like the general flow of the arguments, I'm kind of following off here, but it's drawing off work that's been done other places as well. Okay. So I'm gonna, well, I guess for the moment I won't erase it. We'll just move on. Okay, so now we want to move on to LOCC. Okay, and there's going to be one major theorem that we're going to use, and this theorem is from, actually it's from another Duan paper. So this is from Duan in, I think, 09, maybe. That year might be wrong, but this is a PRA paper. And this theorem is going to be a generalization of the Walgate result from 2000. And it says the following. So a set of two-qubit states. So we'll say these are rho k. Can be perfectly distinguished by LOCC with Alice measuring first. With if and only if we have this following decomposition. So we have rho k. We can write it in the following form. say this is M00, and we'll put K up here, plus 1, 1. Yeah, K, and then plus some remainder term. And so what does this R look like? Well, this is not really important for our purposes, but this will be something that is like something maybe M01 plus 1. It's essentially the off-diagonal part, M10. And of course, this would be Hermitian. So those are Hermitian conjugates. OK, so it must have this form. And now the key part is that these will be orthogonal for different K. So we have that trace of M00 K, M00 K prime is 0. Sorry, 1 here, 1, 1. Is 0 if K is not equal to K prime. Right, so you can see that this is somewhat like a Walgate decomposition, except here we have mixed states. And so what we're saying is that there exists some basis for Alice, okay, this 0, 1 basis, and then on Bob's parts, there are orthogonal parts between the states. That's what this is saying here.
K equal to K prime
K,
would be 1. Looks like
maybe
1 because trace of rho K must be 1.
but I mean it could be no. I mean there could be some coefficients there. If K is equal to K prime, it doesn't need to be 1. Right, I guess the sum of it would, if you took the sum, yeah. Okay, so why is this sufficient for distinguishability? Well, again, the protocol is the same as in the Walgate case. What Alice does is she measures in this 0, 1 basis, and then what will be left is if she gets a 0, there'll be a set of these reduced states on Bob's side, but they're all orthogonal, so Bob can just measure. Right, he can distinguish these because these are orthogonal states. So you can perfectly distinguish them. OK, so we're going to quickly go through the proof. The proof is pretty simple on this. And it'll be good because you can. The idea here gives a little flavor in how these distinguishability theorems are derived. Oh, and by the way, OK, so there's this condition I said with Alice going first. The other option is, of course, if Bob goes first. And then we'd have to check for a decomposition on Bob's side as well. Right? So I mean, if you were just given a set of rho K and you were asked, can you distinguish these by LCC, what you would have to do is you would have to first search for a decomposition like this on Alice's side, and say you couldn't find one. Then you would have to go on and check for one on Bob's side as well. And if you couldn't find one, then no, then you can't. OK, so the key part to this proof is that because we demand perfect discrimination, that's what we want to achieve, orthogonality must be preserved. Must be preserved after each local measurement. And this is kind of a key property because when we're making this comparison between separable operations and LLCC, we don't really have a constraint like this. Because in a separable operation, it's just you're performing a POVM, a two-sided POVM on Alice and Bob's side. But in LLCC, you have to build it up by first Alice measuring, then Bob measuring. And so that's a key difference. And the constraint is that after each measurement, and we look at the post-measurement states, they must remain orthogonal. Because if they're not, then there would be some probability of error. Right? So this is a very strong constraint. OK, and so let's see how this plays out. So suppose that, say, alpha lambda are Krauss operators. For Alice's first measurement. Okay, this is her round 1 measurement. Again, we're assuming Alice goes first. Okay, and let's consider then any psi k that's in the support of rho k, and any psi k prime that's in the support of rho k prime. All right, and what must happen is when, for each outcome lambda that Alice, yes?
So you have considered here the state of the states. So this state is continuing only 2 states?
Sorry?
This state, you have
The rho k here?
yeah.
Well, I mean, in principle, you could have consider a large number of them, but you would have to have this decomposition. So I mean, okay, so actually this is, I shouldn't actually say 2 qubit. This actually holds for 2 by n, right? So this result will hold for 2 by n as well. But then it's a little bit different, right? Because then it certainly matters that Alice is the first measuring party. Okay, so it's whoever has the qubit side has to be the first measuring party for this to really for this to work. That's why by 2, then you can just say, well, it's got to be either Alice or Bob, right? Okay. Yes.
Neglecting the R part, if we neglect the R part, R,
Yes.
the expression, then rho k is like classical quantum state.
Yes. Mm-hmm. Sorry.
If we take the 2 cross n state,
Yeah.
then also Alice need not make the first measurement.
Yeah. Right.
Any one of them can be chosen. Is that right?
Well, okay. So if we're taking the 2 cross n and we are considering Bob going first, then we can't say anything. So, I mean, it would be possible that if Bob's going first, the states wouldn't have this form. They'd have some other form. Yeah. So that's why, I mean, it's sort of artificial because here you're sort of, this is a condition only under Alice going first, right? Yeah. But again, for 2 qubits, that's fine because it goes either way.
But in the Walgett paper
Yes.
of 2000, they have considered only 2 states, right?
Actually, in the 2000, yes. In the 2000, it's 2 states, but in the 2002, they do more states. Yeah, they consider 2 by n. Actually, I mean, the only difference between, if you go and look at this paper, the only difference is that they consider pure states, whereas this is mixed states. But I mean, the argument here is identical. It's exactly the same. All right. Okay, so we have this, and now the condition is that after we perform, Alice performs this measurement for each outcome branch lambda, the post-measurement states must remain orthogonal. So originally they're orthogonal because they're in the support of different states, rho k and rho k prime, and these are originally orthogonal states. So after the measurement, they must remain orthogonal as well. So we can write this condition down. Right? This is just saying, so, I mean, the post-measurement state of k will be a lambda applied to k. Sorry, this would be k prime. And so we're taking the inner product between the two. And then likewise, we have the original orthogonality condition. And this is for all k not equal to k prime. Okay. So what we're going to do is we're going to show that this is going to force a lambda to be trivial. Okay, and the way it works is we can look at a lambda dagger a lambda, and we just take a spectral decomposition. So these alpha 0 and alpha 1s will span our space. And, let's give this guy an eigenvalue. Okay, and now assume that alpha 0 is not equal to alpha 1. Otherwise, this would be just the identity, right, or proportional to the identity. So we're not going to, we want to consider a non-trivial action by Alice. All right, so this is the assumption we make. And now what we'll do is we'll expand psi k in this basis. So we can write this as alpha 0 and call this beta 0k plus alpha 1 beta 1k. Right? We can always do this. And then likewise for the k prime, we do the same thing. Here's the k prime. Okay. And now what we do is if we just substitute this in here, I mean, we have these three parts, right? So we had this decomposition of A lambda dagger A lambda. Throw this in here. And we know that these are orthogonal, right? Because they're eigenvectors. This is a Hermitian matrix. It's a positive matrix. So when we just make the substitutions in there, what we get what comes out is that we have 0 is alpha 0, beta 0, k, beta 0, k prime, plus, and then we have this other part here, alpha 1, beta 0, k, beta 1, sorry. Beta 1, k prime. Right, so that's in the first one, and then the second one gives us just that beta 0, k, beta 0, k prime, plus beta 1, k, beta 1, k prime. Okay. And so now you can just solve for this. If you just, for instance, substitute the second into the first, you get that. So this implies then that 0 is beta 0 k, beta 0 k prime times alpha 0 minus alpha 1. Okay, and remember our assumption that alpha 0 is not equal to alpha 1, right? So this can only be true as if this is 0, which means that these are orthogonal, right? And remember, this holds for any k, any psi k in the support of rho k, and any psi k prime in the support of rho k prime. So that means that in this decomposition, we must have that these are orthogonal between the different k and k primes, right? Because if any state when you write it out like this, any state that's in this decomposition lies in the support of rho k, and what we're saying is that actually any state in the supports must be orthogonal on Bob's side. Sorry? Alpha 0 minus alpha 1? Okay? All right. Okay, so this is good. Right, so we proved the necessity and the sufficiency is obvious by just the protocol. Okay, so now let's use this and let's consider the different cases. Okay, so the first is now this 1-1-1 case, right? And this comes right out of this paper, the Walgate and Hardy paper. But again, this generalizes that, so we get it. We get it as well. All right, so we know that using this structure theorem, that if we have psi 1, psi 2, and psi 3, right, that we must be able to write it in this form. Choose it. x1 plus 1 y1. Right, there's some basis for Alice, this 0, 1 basis. And now the constraint is that these guys must be pairwise orthogonal. Right, so we have that. Oops. We have that xi, xj is equal to yi, yj is equal to 0 for I not equal to j. All right, and now here is really where we use the fact that we're in 2 qubits. So this was for 2 by n, but now we want to really use 2 qubits because this is sort of just like a packing type idea, because we know that Bob's system is only 2 dimensions, right? So we can't possibly have 3 pairwise orthogonal states unless they're both the same, unless at least one pair is the same. Likewise, we can't have 3 orthogonal states. The y's can't be 3 distinct orthogonal states, so you must have 2 being the same. But these also must be orthogonal amongst themselves. Okay, so that's quite a few constraints on it. And well, if you think about how all those constraints and putting them together, the only way that this is possible is if it takes something of the form, say x like this, and psi 2 then actually must be a product state where this x is orthogonal to that, and then psi 3 is like this, y perp. So it satisfies the conditions that they're both pairwise orthogonal. Okay, so this is the only possibility, the only way you can satisfy this condition in 2 by 2. So 2 by 2 implies this. And again, it just goes back to the fact that Bob's system, I mean, you can't have more than 2 distinct orthogonal vectors. Okay. So, I mean, right. So basically what this is saying is that to distinguish 3 pure states, 2 of them, at least 2 of them, must be product states. You can only have 1 entangled state. In fact, this guy could be a product state as well. If y was 0, then you'd have 3 product states, which makes sense that you can distinguish those. Okay. Case of 1, 2, 3, 4. Well, you apply the same arguments. So now we want to add another guy here. And then there's 2 ways to do it. You can quickly see it as if you just added a 4th state here, you just apply the same arguments on all sets of 3, right? And what you'll find is that you must have them all to be product states. So in that case, the most general distinguishability ensemble will look something like this. Let's see how I want to do it. 0x dagger, 1 y, and then 1 y dagger. All right. Yeah, one thing to note about this is the x and y's themselves don't need to be orthogonal. Okay, so that's something that's important to keep in mind. So here, I mean, we're really setting this up for Alice measuring first. Because, I mean, the protocol, again, is obvious. Alice measures 0, 1, and then Bob just, if she gets a 0, she announces it to Bob. And then he says, all right, so I measure in the x perp basis. She gets a 1, he measures in the y perp basis. So the communication is essential for this. I mean, you could also consider an ensemble where you swap the Alice and Bob roles, right? So you have the 0, 1 on Bob's side, the conditional basis on Bob's side, and then Alice has the conditional orthogonal basis. Right. I mean, yeah, likewise here. So again, this is favoring Alice, but the same thing holds. You could just by switching the roles between Alice and Bob.
In which case, Bob
Yes. Yep. Yeah.
Both these ensembles are pure ensembles?
Yes. Yep. At this point, we're just doing pure. Okay. So now we consider the mixed. So I'll tell you the answer to this, and then we'll leave it.
The last one you wrote is essentially unique modular local unitary, is it?
Yes. Yeah, and the swapping, too, between the parties. Yeah.
But this one, the 3, it may not be unique.
No. So unique, you mean?
Modular local unitary on the Bob side.
Right. Yeah, right, no. It wouldn't necessarily be unique in that sense. Okay.
Remain entangled now. Has to remain. Psi 1 must remain entangled.
Okay, yeah, so I mean, no, I mean, psi 1 doesn't need to be entangled. So that, I mean, so there's example there. Right. Okay. Okay. So for the 1-2 case, I'll give the answer, and then as an exercise, I challenge you to do it because actually the argument is almost identical to the 1-1-1 case, and we can, so you guys can think about it over lunch, or whenever, and then we can check it in tutorial. Right. So the condition is that so if your ensemble is psi and rho, LOCC can perfectly distinguish if and only if the support of rho contains an orthogonal product basis. Okay, and the way you do this, you prove this. I mean, I'll give you a head start on how you think about this. So what you do is, again, I was saying that it's similar to this situation here. Well, let's just rewrite this as these guys as rho 1 and rho 2. So these are going to be eigenstates of rho. Okay, and now, I mean, if we apply the same condition, we still must have that x1 must be orthogonal to those guys. Likewise, y1 must be orthogonal to those guys. So here, I mean, we still have this strong orthogonality condition. Now we just fix this as 1. So whenever I is not equal to, or whenever j is not equal to 1, these must be orthogonal. Okay? But, I mean, we've chosen eigenstates, so these guys must be orthogonal themselves. Right? So that's how you can get to this. All right. Any questions on this? Then I'm going to write down a little bit of a summary of what we've shown on everything. Oh, okay. Well, I mean, so right, there's still these other cases. I mean, we only showed 1, 1, 1, 1, and 1, 1, 2, right? And there's all these differences. But if you remember what I said, that the conditions for separable operations, if you write them down, they actually give you an LOCC protocol. So if you work through all the other types of ensembles, and again, those are the cases where the supports of your state span the full 2x2 space. If you write down those conditions, it'll just give you an ensemble, give you a protocol of how you can distinguish it using LLCC. So the reason I'm not getting into those is, one, they're pretty easy to whip off, and the other is that there's no difference between separable operations and LLCC. The only difference comes in between these two cases here. Okay. So we'll just make a chart. So here's the 1-1-1 case, and the 1-2. And so we'll first recall what the SEP is, conditions for separable. All right, so remember for this, we had this nice concurrence condition. So let's say our ensemble is going to be psi I. This is pure states. The condition, and eta is going to be perpendicular to them. So eta is this state that's in the orthogonal complements of the subspace. So here it was just that the sum of the concurrences I equals 1 to 3 must equal the concurrence of this eta. Okay? And there was also this other condition. When I was looking over my notes, I realized that I didn't emphasize this. I didn't even write it down on the board. But in that proposition, there was this. In order to have the separable POVM, you had to have that lambda was the ratio of the concurrences. But we also had this anti-parallel eigenvalue condition, which was a technical thing, but it was necessary. So the other condition is that you must have that psi I eta inverse has anti-parallel eigenvalues. Okay. Right. Actually, so I'm going to these exercises. I'm going to just keep a list here. So the first exercise was prove the 1-2 case. The second is now, what you can show actually is that this condition, that psi I eta inverse has anti-parallel eigenvalues, is always satisfied if this eta is a maximally entangled state. Okay? So in other words, if you consider a maximally entangled 2-qubit state, then you look in the orthogonal complement of that one-dimensional subspace. So you have a 3-dimensional subspace, and orthogonal to that is a maximally entangled state. And you consider any basis for that 3-dimensional subspace. The only condition that we need to check is that the sum of the concurrences equals 1, right? Because the concurrence of the maximally entangled state is 1. So we just need the sum of the concurrences of the basis states to equal 1. And I claim, and this is what I will write down as the exercise, is to prove that this second condition is always satisfied as long as the eta is maximally entangled. So has anti-parallel eigenvalues when eta is maximally entangled. Okay, so this was the condition. And so then we had, for the 1-2 case, we have our ensemble will be, say, psi and rho. So psi is the pure state, rho is the mixed states. So we have two options. One is that psi is a product state. Or, so if it's a product state, good, we can do it. Or we have these two conditions. One is that, again, that this psi, well, the concurrence of psi is less than or equal to the concurrence of eta. And 2 is that this psi eta inverse has anti-parallel eigenvalues. Okay, again, this anti-parallel eigenvalues may not be like standard terminology. It just means that, so Z1 is related to Z2 by some beta, where beta is less, okay, hold on. Because I was calling the eigenvalues beta plus, beta minus. So beta plus is equal to beta minus by some kappa, and kappa is less than 0. That's what we mean by anti-parallel. Okay, now let's compare it to LCC. And so what we showed here is that at least 2 of the states must be product states. Two of the psi I are product states. Okay, and then for the 1-2 situation, we have that this support rho contains an orthogonal product basis. Now, if you go back and review that proposition 2, or proposition 2, the main proposition that we proved, there was a corollary to it, and the corollary was that if you have an orthogonal product basis, then you have the concurrence is the same for any 2 basis elements in that subspace, orthogonal basis elements in that subspace. And so, and you have this anti-parallel condition as well. So here it's that either psi, did we have that? Sorry, I guess I didn't put this here, but if psi is a product state, this is a sort of a trivial case. This is or. There's 2 possibilities. Either psi is a product state or the supportive rho has an orthogonal product basis. So psi is a product state, or again we have this eigenvalue condition. Well, I'll put that 2 at psi eta inverse has anti-parallel eigenvalues, but now instead of this less than or equal to and the concurrence, they must be the same. Remember, that's what the corollary said, is that if it has an orthogonal complement, that the 2 states must have the same concurrence. So here it's concurrence of psi must be the concurrence of eta. Yeah, so I think if you write it like this, it's kind of nice because you see it really comes down to this concurrence. So here, when you have equality satisfied, you can do it by LCC. Yes?
What is eta in the second?
It's still this, or it's still, okay, yeah, it's orthogonal to both of these. This is a rank 2 state. So it'll still, the support of both these guys, the union, will be some 3-dimensional subspace.
So does that mean that I actually can also distinguish eta in the row, no?
In which case? The LCC case?
Yeah.
Yes. Yeah. Okay. And so now we can look at some examples. So we write, let's write gap here. So we want to find some that's are satisfied by SEP but not by LCC. Okay, and well, I mean, you can find a whole bunch. I mean, because really this is pretty strong that the 2 are product states, but this is weaker. You just have to have this concurrence condition. And so the one I'm going to show is one that is given in a paper. So this is by Kleinman and Kapperman and Bruce. This is in PRA. This is 2011. And, well, okay, so it looks a little nasty. but it works nonetheless. So one of the things that's interesting about this is that one of the states is a product state, but of course, and the other two must be entangled. Otherwise, we could get it with LCC. And it looks something like this. So it's proportional to, let's see if I get this right. And then you have this you have 3 to the 1/4 and 1/1. And then psi 3 is of this form. So if you were to calculate the concurrence of these guys, you'd find that it would be 1/2, because line in the orthogonal complement of this is a maximally entangled state. Okay, and I draw your attention to this. I mean, I write down the details here because actually, when we talk, we're going to get to the question of asymptotic LCC discrimination. And in this paper, where they look at the asymptotic case, they derive a necessary condition, and they show that this satisfies the necessary condition. So a necessary condition to distinguish perfectly by asymptotic LCC. And this is one example that they showed that satisfies their necessary condition. So in other words, they can eliminate distinguishability of this by asymptotic LCC. So this I think is this ensemble here and ensembles like it. It's one that I've tried to solve. I'm after it, but it's an open problem, and we'll discuss that a bit more.
What does gap mean?
Gap. Okay. Yeah. So this is distinguishable by SEP, but not LCC. And again, what I was just saying is that distinguishability by LCC closure, LCC bar, is not known for this ensemble. That's why it's an interesting candidate. Okay, and so now, right? So now we want an example here. Well, let's see. Okay. So actually, this will provide a good segue into where we're going. So we want to find one pure state and one 2-qubit mixed state that we can distinguish perfectly by separable operations, but not by LCC. Okay. Yes?
So, I mean, can we say that one can distinguish between psi and rho? I mean, it is sufficient, I mean, for distinguishing between psi and rho, if you can distinguish between psi and IM vectors of rho?
Yeah, I mean, so as a 3-state ensemble, certainly, yeah. That's a harder problem.
Yeah, that's why it's sufficient.
Yeah. Right. Okay. So, right. So to get an example here, I'm actually going to generalize the problem a little bit. And the reason I'm doing that is because we're going to look at minimum error discrimination after we're done with this little chart here. So with minimum error discrimination, here we're not necessarily dealing with orthogonal states. So here we might have psi and rho may not be orthogonal. And what I mean, in case you're wondering what I mean by orthogonality between a mixed state and a pure state, just look at the support of rho, and psi lies in some orthogonal subspace to the support. So that's what I'm saying here. Okay, and so the way that you want to calculate this is, actually in tutorial yesterday, we talked about this a bit. So for those who were there, saw this. So, but I'll just review again. So the minimum error. Now this is if we're allowed to perform global operations. So just take a step back from the LCC setting. And this is now if we allow global operations. So the minimum error probability. What we want to do is we're trying to minimize our error. And we're going to perform a 2-outcome POVM. So this will be psi and rho. And we want to minimize this quantity here. So I mean, with full generality, we can suppose that we're given psi with probability, let's call it p psi. Okay, so this is like the a priori probability. And we're given rho with probability p rho. Okay, the p's hopefully. So when I write my p's, I'm going to use like cursive, so there'll be curls, and the rho is not. So that's, sorry. Right. Okay. So here.
Means that the eigenstates rho
Yes.
will have two different p's.
No. Well, okay. I mean, but that's probably not the best way to think of it. Think of rho as coming as one package, and that whole package is coming with probability p rho. Right? I mean, if you wanted, I guess you could fine grade it in terms of the eigenstates, but here we just want to know whether or not we have rho. Okay.
So now that you want to allow error, you necessarily have to have probabilities.
Yes. Right. Yes. Yeah. Even with global, right? Okay. Right. So the problem is then we were minimizing. Let's see. We're trying to find a POVM, and we want to minimize this minus p rho of trace of, shoot, this is actually the other way around. So, oh no, that was right. So I mean, we're minimizing error here, so we want to take 1 minus the success. So again, this works is when you perform this measurement, you get outcome psi, you guess psi, you get outcome rho, you guess rho, naturally. All right, and so this actually,
And why do you have this one half there?
because, guess we don't need it. No, you're right. You're right, yeah. Because here are the p's there. Yeah. Yeah, just 1 minus. Okay. And the way that this can be solved, and the way it works is you look at this difference operator. So call this, I guess, omega. Right? And this is a Hermitian matrix. And so we can look at a spectral decomposition. So I can write this as R plus minus S minus. And so here, R plus and S minus are positive matrices. And they're also orthogonal. Okay, so this is we've just done a spectral decomposition here, and we've grouped all the positive eigenvalues together, and we've grouped all the negative eigenvalues together. Okay, and so then the optimal POVM is just going to project into the eigenspace of rho plus and S minus. Our projectors. Onto the support of R plus and support of R minus, or S minus. So another way of thinking of it is you're just going to project onto the positive and negative eigenspaces of this this difference here. Okay? And so what bearing does this have on everything here? So the observation then is that LLCC, so again, this is with global operations. So these POVMs can be anything. We're not talking about LLCC here. And the consequence then is that LLCC can obtain the global optimal probability if and only if we can perfectly distinguish R plus and S minus can be perfectly distinguished. By LLCC. So essentially what this does is it reduces the problem of discrimination of non-orthogonal states to a problem of distinguishing orthogonal states, right? Because these guys, that's maybe not clear, these guys are orthogonal. Okay? So, right, so what I want to do then is,
Small puzzle.
yes,
The minimum you set up.
yes.
1 minus psi minus etc. So I thought omega would be plus. So 1 minus omega.
Say again?
I would have thought since you
Oh, okay, right. But I mean, you have this. If you work this out a bit, so you know that these sum up to the identity here.
now I see what
Yeah. So you'll get stuff to flip around. Yeah. Okay. Right. So again, I wanted to give an example here of orthogonal psi and rho that cannot be distinguished optimally by LLCC but can by SEP. And the way I'm going to do it is I'm going to build up a pair of non-orthogonal states, and then I'm going to look at this difference operator, and that's going to be our example. Okay, so it's kind of going about it like roundabout, but it's good because we're going to talk about this problem next, so it fits right in. Okay, and this construction is in the, well, I erased it now, but it's in the archive paper. So this is in the 13081737. Okay, and it goes like this. So we're going to consider psi just be the product state 0, 0. I guess we were calling this phi plus. Zero, 0 plus 1, 1. And then we're going to introduce a state S theta. So theta is going to be some parameter. And this is cosine of theta, 0, 0 plus sine theta of 1, 1. So this is just theta is giving you your Schmidt coefficients there. And now I want to form the mixed state. Rho theta is going to be 1 over 1 plus sine of 2 theta. That's just the normalization there. And it's going to be mixing this and this. S theta plus then our EPR state. Oh, we want a coefficient here. We want sine of 2 theta here. Okay. Now, why am I interested in this? Because if you look at this state, the concurrence of S theta is sine of 2 theta. Okay, and so we know that this state rho is separable because of that proposition that we had. So rho is separable. And now the problem is that I want to distinguish optimally between 0, 0, the psi state, and rho theta. Okay, so I want to perform optimal discrimination between two separable states. So there's no entanglement at this level, right? Because this is, of course, we got a product state and we have a separable state. But they're not orthogonal, clearly, because this is, I mean, it's all living in the 0, 0, 1, 1 subspace, right? So this is what we want to distinguish, and we can assume like their probability 1/2. And so how do we do that? Again, we look at this difference operator. Minus rho theta. And what you get out is some of, I don't know what to call it. Well, let's just call it some pure states, phi, let's say. And then minus some omega, I guess. Okay, and the claim now is that these two, so these are orthogonal, right? Because we've done this spectral decomposition of this operator, and this is the positive eigenspace, this is the negative eigenspace. And so rho and omega and phi are orthogonal. But actually, you can check it that they don't satisfy this condition. So if we look in the orthogonal complement, right? So the orthogonal complement of all this is actually psi minus or phi minus. Wait, is that right?
Eric,
Yes.
at the bottom, have you written that rho is separable?
Yes, it is. Yeah, this is what separable means. Sorry.
So, I mean, it has, it's a mixture of 5 plus, and then
It's this guy and this guy.
and the other guy is the filtered 5 plus, right? How will it be? I mean, I'm not able to see that it's separable.
Right. I mean, it's not exactly obvious. That's why you need to use the fact that the concurrence of this is sine of 2 theta, and then you use this proposition that we proved that if you look at a mixture of
To me,
Did I?
I mean, I don't think it will be separable for any value of theta. Unless your sine, I mean, sine theta is minus cos theta.
No.
Unless, I mean, except for theta equal to 45 degrees, this is not separable.
No, this will be separable.
Oh, that is 5 plus, is it?
Yes.
Oh, sorry.
Yeah.
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 See, this. Okay.
Not comfortable with it?
See, if you look at the 2-qubit density operator,
Yes.
it still has only the corner entries non-zero, is it not? I mean, for S theta, only the corner entries are non-zero.
And
for
the
pi
corners?
plus,
The corners will be non-zero,
Yeah.
but that may not be bad.
Maybe I'm reading different.
The decomposable form. It's very decomposable form. It's summation field.
I don't know what the decomposition looks like.
Okay.
But we're just using this fact that we proved in general.
No, if you take theta is equal to pi by 4, this theta will be same as 5 plus, right?
Yes.
And sine 2 theta will be 1. So this is basically this projectional pi.
Yeah. I mean, if you take, it's the same thing then.
Then it is not separable.
No, I mean, see,
No. Okay.
Put
Wait.
a minus somewhere.
Yeah. Hold on. There's something. I don't know.
I mean, as you have written, as it is written, it is separable only for theta minus 45, minus 54. I mean, if my eyesight is doesn't.
Okay. Wait. Good. There's something not right on the board.
No, but theta cannot be negative.
Because you're right. If you choose theta to be pi over. Oh wait. Maybe we limit the range of theta.
No, that's not separable state for any value.
Okay, so we will return to this. So at the moment, so what I'm going to claim is that this decomposition here, this phi and omega belongs in this block here. So here I want to say that this is phi and omega. Okay, and so if we just clean this up, there's something's not quite right there, but we'll return. Okay, good. All right. Okay, and then so now we're actually going to change subjects a little bit. Well, not change subjects, but get out of this, move on, because there's a question mark here. If we want to consider this asymptotic LOCC here, and now we ask, how does this fit in the chart? Here we have just question marks. Okay. So we know, and barring a few examples, a few cases, we can definitively, on an ensemble by ensemble case, we can determine its distinguishability, but we have no general criterion like this. And so this is a problem I'm definitely interested in because I feel like it's sort of the last remaining piece to the whole 2-qubit distinguishability. So, I mean, we have almost everything figured out. And so what we're going to do for the rest of today and most of tomorrow is we're going to explore what distinguishability looks like in this LOCC asymptotic, the closure, how you actually go about analyzing this. So I'll chart out one strategy. That's what we're going to do. But let me just explain why this is difficult, right? Why we have troubles here. So remember in that proof, we use this fact, and I highlighted it then, but maybe you can appreciate it more now. So when we were looking at, we had the psi k, and then we had the psi k prime, and we demanded that when Alice performs some measurements A lambda, well, we said that the post-measurement states must be orthogonal along every single lambda. But now, if we're looking in this setting here, we're going to allow an epsilon error, right? I mean, epsilon, we can control how small epsilon is, but it'll be non-zero. And so we can no longer use this nice orthogonality arguments that's applying that after every single measurement, you must preserve orthogonality. You lose that, which makes things difficult because, I mean, then it was just basically sort of linear algebra, and we had this trying to fit orthogonal states in a two-dimensional subspace, and I mean that was very sort of simple to analyze. But we lose that rigidity when we allow epsilon error. Yes.
Why do you want to use that condition? Because your goal is to distinguish them.
No. But when in this setting, the way it works is as follows. So it says for any epsilon, you can find a protocol that errors with probability less than epsilon. It doesn't need to be 0, but you just need to find some probability that errors with less than epsilon. Okay. So then we could, I mean, we could break orthogonality, but it could be by very small amounts. It would be epsilon over 2 in some sense. All right. So to motivate this problem, actually. All right, so we're moving on to this, but I also want to make another comment, and we'll see how these two come together. In all of these cases here, when there's the gap between SEP and LOCC, it involves entangled states. Right? You can see here we needed some entanglements here, and also in this phi and omega, if we go and calculate it and we do it properly, you'll see that the phi and omega are entangled. Even though I was claiming that those two original states were separable, when you look at this omega operator and you decompose it into its orthogonal parts, these in general will be entangled. Okay? So what I'm getting at is that if you don't have entanglement in your ensemble, you have no gap between separable and LOCC in terms of perfect distinguishability for 2 qubits. Okay? And so we want to build up to this, as you guys have heard, this non-locality without entanglement. Right? This is a pretty interesting topic. And so if you want to look for that, well, you need to sort of look beyond 2 qubits, because as far as perfect discrimination goes, because you're not going to find it in the problem of perfect discrimination. Okay, and so where do you look? Well, let's return to the paper that coined that phrase and gave us the first example. So this is it's a 2000 or 99 paper. This is well, a whole bunch of guys were on this. And this is titled Non-Locality Without Entanglement. This is PRA 99, I think. Yeah. Okay. And so here they're going to consider a 3x3 system. All right. So now we have qubits, and we want to consider a basis for this, a full basis, complete basis. And so the states we're going to look at, the basis, I'm going to write all 9 down. Right, it's 3x3, so there's 9 states, and then I'll give a picture. And once you see the picture, you won't ever forget the states. You might forget the numbering, but I'm not going to include normalization, so these will be unnormalized. And 0. Psi 5 is. So the way I'm ordering this is if you see an odd, it's going to have a minus sign. If it's an even, it's going to have a plus sign. So this would be 1 plus 2, 2, and then psi 7. 1 minus 2. Well, maybe it'd be better. Just psi 8 is. Oh, 2, sorry. And then the last one is the minus. Okay, so like I said, the picture, right? So these are sometimes referred to as the sausage states, or the domino states. So the way to think about this looks something like this. Okay, and so put Bob up top here, and Alice here, and so 0, 1, 2, 0, 1, 2. Okay, and so you can see how this works. So psi 1 is here. This is the 1, 1. And then in this block here, so Alice is 0 plus 1, and oh boy, maybe I drew it wrong. Well, okay, so we have to rotate a bit. Just rotate our dominoes. Like that? Yeah? No? Wait. Like this? Like that? Okay, good. Yeah, okay, so this would be the psi 2 here, and then psi 3 was also going to be you switch the phase, and etc., and you fill it out like that. Okay, so third exercise, and this is the most important one, I think. If you're only going to choose one of these to do, prove that these cannot be distinguished, indistinguishable by LOCC. Okay, and here I mean perfect discrimination, 0 error. And this is not that hard to do, again, because you can invoke one of these arguments, one of these orthogonality arguments, that you consider Alice or Bob performing some local measurements, and every outcome on that measurement, they must be orthogonal, the post-measurement states are. So you can just do that, and it's a good exercise to do, and you can show that actually this is impossible to prove it. Now, but the much more difficult question is if you want this asymptotic LCC, right? And here the question again would be something like, I'm going to give you an error threshold of epsilon, and I want you to identify which state you've been given within this probability epsilon, right? Okay, and so and they proved that in the original paper. They proved this case, the LCC bar. So what I want to do is I actually want to reprove that result using some different techniques than what they used in that original paper. But at first I want to just write down a list of references that have kind of spawned off this on the topic of LCC asymptotic discrimination, okay? Because this is sort of a relatively new class of problems. And so if you're interested in this, so that Kleinman paper I wrote down, Kleinman, this is a PRA 2011, and they actually prove. So okay, so the answer here is LCC question mark is no, you cannot discriminate asymptotically, and so they prove this result as well in this paper. So they return to the problem, and then there's a few other papers. So this is 1312. 06. So both of these have an overlap of authors. Laura Mancheska, and Andrew Childs, Debbie Long, and Maris Oslos. So they got interested in this problem, and they derived a number of results extending on not only this problem, but just studying LSCC asymptotic in general. And then also the paper that we taught on the first lecture when we derived this framework of LSCC, that paper discusses this as well a bit. Okay. So, all right, so what we're going to prove, we're going to look at, is we actually want to show something stronger than this, that these can't be distinguished. And what we're going to look at is we're going to consider the problem of distinguishing between two mixtures of these. Okay, so instead of being a 9-state discrimination problem, it's going to be a 2-state discrimination problem. And our states are going to be tau 1, and we're going to sum up, n is even, so it's be psi n, and tau 2 to be sum up over n is odd, okay, and so let's actually write this down in exercise 4. So prove for any other mixture can be distinguished 2-state mixture now by LCC. Try to design a protocol that does that. All right, and so, okay. So we'll break up the proof here over today and tomorrow. But the first thing, so today we're just going to describe some preliminaries, some tools that we'll need. And I think these tools are again, general. So even if you're not interested in this problem, if you're interested in LOCC in general, you might be able to use them elsewhere. So, okay.
So by any other mixture, you don't just mean partitioning these 9 positions.
Yeah, that's what I mean.
But you can even introduce relative probabilities in all the...
Yeah, right. Yeah, exactly. Right. I mean, the thing is, because the probabilities, because ultimately we want in the limit of this, we want absolute discrimination, perfect discrimination. The probabilities don't really matter, right? Because if you're free to change them, but if you demand perfect discrimination in the limit, then it doesn't matter. Yeah, okay, so these are just some general tools. Let's see. Okay, so first, we want to have, so I wrote down before this minimum error, what did I write? Probability. So I think I wrote that the probability, minimum error probability, and this is by global. So we had that expression before. Well, okay, so it's I didn't write it in its form, but it's just 1 minus p rho minus p sigma, and it's just the one norm of this matrix. Remember, we called this guy omega before, and that when you do that spectral decomposition, you're actually just looking at and then you project onto the positive and negative eigenspaces. You're actually just adding up the singular values. So that's why you have this one norm here. Okay, and that was for global. So now what we want to have is we want to talk about an LOCC error probability. Okay, but now we need to be a little careful because remember when we defined this over here, we had a minimization over all POVMs. But the problem is that that minimization really only makes sense if the set of POVMs that you're considering is a closed set. Yeah. This is the minimum error. Minimum error by global operations, global measurements. Make sense? Yeah. Okay. Yeah. Right. Again. So, but again, this minimization. If we want to talk about LOCC and we want to restrict ourselves to LOCC POVMs, we can only really do this minimization if we look at the closure of LOCC, right? Because otherwise, the minimum might not exist. You would really need to look at an infimum, or you can just say, I want to consider the class of LOCC bar and then minimize over that. Okay. So that's in order to really talk about minimum error discrimination in the LOCC sense, you're actually always talking about this closure bit here, right?
What precisely is meant by global here?
Global, I mean, the most general POVM. So you think this is...
Not necessarily LOCC.
No, exactly, right? This is a two-part system, and you're free to measure across it, all acting in the same lab.
There maybe will not be the half vector.
The half? This time it is because we're taking the norm here.
You are taking this definition from the previous one.
Yes.
Previous one there was no norm. Previous one there was no norm.
Right. Yeah, that's right. Yeah, because we just wrote it out in terms of the traces last time. Okay. All right. And so one thing we can use is this nice bound on this guy. we can, an upper bound actually, and P rho, P sigma, sigma, we have this upper bound in terms of the trace between the two. P rho, P sigma, and the trace between rho and sigma. Yeah. So this is going to be useful for us. It's not actually necessary that we use this bound, but ultimately this is going to give us a lower bound on our error, right? So we can actually say that this is then lower bounded by 1 minus the square root of the trace of rho sigma. Right, so the whole idea here is we have a way to lower bound our error probability in terms of the two states, their overlaps. Okay, this, if you want to see this is well, you can prove it yourself. It's not too difficult to do. Or I know in Nielsen and Schwang they give a quick proof of this. So yeah, okay, right. And so then actually, because we know that LLCC is more difficult than global. I mean, it's a restricted set of POVMs. We can say that this actually lower bounds the LLCC error probability. So here we'll write LLCC error. Right? I mean, this is just saying that we can always do better with global. So we have this lower bound on our LLCC error probability. So this is the first tool we're gonna use. Okay, and then the second, and this is just a very general idea. So if you're given an ensemble, so suppose you're given the ensemble P rho, rho, and P sigma, sigma. So the rho and sigma, these are your a priori probabilities, right? And now you make some measurements. You learn some information about the state based on your outcome. Okay, and then you want to ask, well, you want to update your probabilities. Right? Given what you've learned on your measurement, you want to reassess the probabilities of your states. And so, so you make some measurements, and this reevaluation is known as Bayesian updating, because basically you apply Bayes' rule. And I mean, it's the formula is given as follows. So if m lambda are your measurement cross operators, right? Then of course we have that p psi given rho. This is the probability of outcome psi given rho is just this. This is pretty basic stuff, but I want to just show it in case you haven't seen this before, because what you're doing in this LLCC protocol is you're going to make measurements and you're going to update your probabilities after every single measurement. So just to write this down. Okay, and now we can invert these. So we've made our measurement, we've learned lambda, and now we want to assess our a posteriori probabilities. So now we want to reassess it. So we want to say, what is p rho given lambda? And well, this is just going to be p psi given rho times the a priori probability of p rho. This is just Bayes' rule here over the probability of p lambda. And then this is just trace m lambda p rho over now. The p lambda is just going to be the sum of these guys. Rho times p rho plus p sigma trace. Okay, again, this is fairly elementary stuff, but just so you can see it and get familiar with it. All right, so what we've done then is we started on at one point, before we made our measurement, we would say the probabilities were p rho and p sigma. We've made our measurement, now we have an updated set of probabilities. Okay, and so then the last tool, and then so we'll do this, and then we'll call it a day. Right, so we had this bound on our error probability. We have a way to update our probabilities, and now we need a way to yeah. Yeah. I mean, maybe.
You update every time.
Yeah.
So does it happen that one of them goes to zero and like that?
Maybe.
You update here to distinguish between these.
Yeah. 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 That's not a problem. That's what you want, right? I mean, that's essentially what you're wanting to do is you want to update it to a point where, again, originally, we will assume that these are 1/2, 1/2. All right? It's a coin flip to begin with, and you want to update it so that one goes to 1 and one goes to 0. Yeah. Okay. Yeah, I don't know. I mean, it's time now. Are you guys cooked? Okay, good. All right, so this is weak measurements. Okay, so this is just a prescription of a way to take an arbitrary measurement and break it up into a series of small measurements. And the reason we want to do that is because when we're looking at this LOCC protocol, in general, it's just going to be back and forth measurement. But we want to keep track of this, how these probabilities are updating, and we want to do it in a continuous manner. We want to say that if it jumps from one probability to another, we could actually have modeled the protocol in terms of a sequence of weak measurements and stopped it anywhere along that path, along that jump. Okay, so this formalism, it's been done a few times in the literature, but the one I'm going to talk about is from that Kleinman paper, because I think it's probably the easiest. 2 ends maybe. And this is, again, 2011. They call it pseudo-weak measurement in that paper. And so the way it works is as follows. So suppose you have your original cross operators are given by psi k. So we're going to introduce 2 new measurements. The first is, so actually I'm going to say pseudo-weak, because that's what they call it, so to keep with their terminology. So the first is going to be the set of pseudo-weak operators, and it's defined as follows. So we're going to have some beta bk I plus mk dagger mk. Okay, now here beta is just like this overall normalization, the sum of the bk. I'll put it like this. And these bk's are going to be parameters. So these are going to be the things that we fine-tune to change our measurement, however we want it. Right. So and so for each k, we have a new operator. And you can see that actually this is a valid measurement if you just sum it up, because I mean with the square roots, if you look at the Hermitian conjugate of this, you'll see that it sums up to the identity. And another thing to note is that this is non-negative, right? Because we just have a sum of 2 non-negatives, and then we take the square root of it. Okay, good. And so then the other operator is, it's actually a family of operators, and these are recovery operators. So RC. So for each k, we're going to get a family, a new set of.
When bk is 0, it goes back to mk, is it?
No. Yes. Sorry. Yes. Yeah. Okay. Right. Good. And a way to think of if you want to say, well, like what is the trivial, then you're actually taking mk to infinity. So as mk gets very big, it's weaker and weaker.
And when bk
Right.
is very large, you're actually doing nothing, almost no much.
Yes, you're doing nothing basically. Yeah. Okay. So this recovery then let's see, is given by beta bk plus delta KL. So yeah, L is, and then we have this ML, and then the inverse. So write this down or check the reference and play around with it, because it's actually quite cool how this works. So this is our recovery, and again, this is a family of measurements. So for each k, we get a new set. So here, this is over L. So we fixed k, and we look at the family of L. Okay, so then in our original measurement mk, what we do is we replace it with a two-step process, and this is why they use, well, I think this is why they call it pseudo weak. So we replace mk by, first we perform the pseudo weak form, and then when we get given k, then we perform the recovery map. So this is again with k fixed. So given k, then we perform the recovery map. Right. Okay, so you can see then what happens. So if we just look at the composition, so first we obtained mk pseudo weak. This was outcome 1. We've applied this to our state. Now we perform our recovery map or measurement, and I'll see recovery here. And you see just the way this is constructed, it's very clever, is because basically you're undoing your first outcome k and you're replacing it with outcome L. Right? So then in the end, what you get out here is just beta times bk plus delta KL and then ML. So it gives you a way to, well, interpolate basically between. So if you have a series of outcomes, right? So if you're going from something like this, what you can do is you can actually break it up into something like, so first you stop here. So this would be one outcome. You've tweaked your BK. So instead of having a full jump, I mean, this is sort of using some, the length here indicates the strength of the measurements. And then when you're here, you perform the measurement again, and you could end up getting to the original possible 3. So it's a way to break up your measurements. And the key thing, actually, and you can compute this, because we don't want this to mess up our protocol. We don't want the probabilities to get messed up. Yeah, so if you compare on average, so now we want to sum up over all the possible k's on our pseudo weak. And we look at some inner product here, ML, you'll see that we get back the same probability as if we had just done, sorry, this is over k here. This is over k. We get back, no, sorry. This is over L. Because it's conditioned on k, then we got L, we get back the original probability. So another way of saying that is here, yeah, oh wait, so we took a side route to get to these, but in the end, the probability of obtaining those 3 are unchanged. And that's actually very important, because if we're messing up the probabilities.
That's what you mean by it.
Yeah.
Because, I mean, there's a common factor, so this whole summation looks good.
Yeah, this sums up to 1, the way.
No. I mean, you have put the same, the psi factor is the same on left and right. So this k summation is.
So there's a k here, yeah? Yeah. Yeah, that's why, because we have this delta k there. Okay. So the probabilities are the same. Okay, and so with that, now we'll pick up on tomorrow. We'll actually put this to use, so we'll apply it in a protocol. Okay? Good.
Don't go away. Some announcements. First of all, Pranab Sen has arrived. So that is good news. And there is some reshuffling of the rest of the program today. So please take a